Welcome to our first lesson in Unit 4. Today's lesson is going to be on atomic structure, where we're going to take a look at individual atoms and the smaller particles that make up atoms themselves. After today's lesson, you should be able to determine the number of protons and electrons in an atom or ion. You should be able to calculate the mass of an atom and the number of neutrons. You should be able to interpret and write isotopic notation, and also calculate the atomic mass of an element and determine the most abundant isotope of that element. Now, to start, atoms we know are the smallest piece that an element can be broken into and still retain properties of the element. Once we start breaking those down further, then the particle is no longer considered an element. And it's going to take this large number of atoms of hydrogen to weigh 1 gram, which is about the mass of a small paperclip. And that number, which is astronomical to try and say, is easier represented in scientific notation, which is 6.02 times 10 to the 23rd of anything, particles, which we'll learn is equivalent to 1 mole, which is also this 6.02 times 10 to the 23rd, known as Avogadro's number, due to Avogadro's hypothesis. Now, nucleons are particles that are inside the nucleus itself, and there are a couple different types. Number one are protons, which have a mass of 1 AMU, which is known as an atomic mass unit, and we'll get into the meaning of that a little bit later. And they do have a charge of +1. Now, the number of protons that are in the nucleus are known as the atomic number, which is also representative of the element. Neutrons have a mass of 1 AMU as well, but they only have a neutral charge. The number of neutrons and protons equals what we call the atomic mass, which is going to be the majority, really all of the mass of the atom itself. And neutrons and protons do not have to be equal, meaning we don't have to have the same number of neutrons and protons in our nucleus. We can have varying amounts. And isotopes, we'll learn, have different numbers of protons and neutrons. Now, the particles outside the nucleus, where we're going to focus on, are electrons, and those are essentially massless. And they do have a charge of -1, which is equal in magnitude and opposite in direction to the charge on the proton. And these electrons orbit the nucleus in distinct energy levels. And for the sake of what we're doing now, we're going to assume that the proton number is equal to the electron number, meaning the atomic number is also going to indicate how many electrons are in an atom of that element. Now, we gain or lose or share electrons to form what we call chemical bonds, or strong attraction between atoms. And there are two main types that we'll focus on: ionic bonds, which are formed when electrons are gained or lost, and covalent bonds, which are formed when electrons are shared. And we get into that in depth in a later lesson. Now, to give you a little example here, we'll take a quick look at an atom of helium. Now, helium has an atomic number of 2, which means it has 2 protons in its nucleus, and it has a mass number of 4, meaning it has a total of 4 nucleons, or 4 protons and neutrons. Since we have 2 protons, we have 2 remaining neutrons to make our mass number of 4. Helium also has 2 small electrons on the outer edge of the atom. Now, this is not drawn to scale. To give you an idea of an example of this scale, and you're going to want to remember this number, the electron's 1,836th the size of the proton. So small compared to the proton that we disregard its mass. And the nucleus is so small that if the atom was the size of a baseball stadium, the nucleus is the size of a baseball. And to take that one step further, if we were to take a grain of sand and put it on that baseball, that would represent our electron. So very small scales here when we're talking about magnitude of the particles. Now, to give you a little other idea to represent our atoms, we said that the number of protons represents our atomic number. which also represents our element. Now we've added one proton here, and we see that we now have our element hydrogen. We can count our particles up here, and the elements highlighted on the periodic table up here. Also note that our mass number went up to 1, and we have a net charge of positive 1 because there's one proton, and each proton has a +1 charge. Now if we continue to add protons into here, we see the element changing, we see the mass number increasing, and the net charge increasing up to +4 because we have 4 protons in here. And each time we add one, the element is changing itself. Now we can add neutrons as well. A couple things to know. Our mass number is increasing. The net charge is not increasing because neutrons are neutral. They don't have a charge. And we can keep adding these in the simulator, kind of as many as you want. But there are certain types or certain isotopes that are considered stable. And this one, carbon, or we'll learn here, otherwise known as carbon-12, is a stable form. But if we were to take away a neutron, it becomes unstable. Or if we add too many, like carbon-14, it's also considered unstable. Now, in order to make this net charge not +6, well, we can't add more neutrons. That's not doing anything. But if we add electrons, we see that one negative electron pairs with a positive proton, and now our overall or net charge changes. And that will continue to go down until they're all paired up to 0, and we can actually add more, and we can go in the other direction. Now we have a net charge of -1. Each time we add an electron, note, the mass number does not change at all because those electrons are massless. And this would be considered a neutral atom. And we'll learn here in a minute that atoms are neutral. So a little bit of information from the periodic table. And we'll break some of this down now and get into some of it a little bit later. The atomic number in the lower left-hand corner indicates the number of protons, and it'll also tell you that 26 protons means that we have element Fe, which is iron. The number in the upper left here is what we call the average atomic mass, which is taking the average of all the different versions of iron, what we call isotopes that are naturally occurring, and we average their masses together, and this is the number that we come across. Electron configuration we get into a little bit later, but this is how the electrons are orientated around the nucleus, and our oxidation numbers, which will tell us the types of charges that iron likes to be when they are combined with other elements in a compound. Now, this is the key directly from your periodic table and your reference table, and it outlines all of the numbers and values that we just went over. Now the note here, numbers in parentheses, are mass numbers of the most stable or common isotope, and you'll see that on your tables that you sometimes have parentheses around the atomic mass, and that's indicating, and it's not going to have it's going to be a whole number, maybe something like 250. It's going to be a whole number, and that's going to be the mass number of a most stable or common isotope, because all of the ones that are in parentheses are considered unstable and have no naturally occurring stable isotopes. We'll get into this relative atomic mass shortly, but this is a good spot to reference any information as you need it on your reference table. All of the elements on the periodic table are arranged by this atomic number, and we read that kind of left to right and up and down. Upper left would be atomic number 1, and they increase as we go down and to the right. Again, the atomic number is the number of protons that an element has. Now, atoms, when we talk about atoms themselves, atoms are neutrally charged, which means that the positively charged protons have to equal the number of negatively charged electrons. And as long as we know the number of protons, the atomic number, which we would know if we know the element, then we can also determine the number of electrons. And that works in vice versa as well. If we know the number of electrons that we have, then we also know the number of protons, as long as we're talking about neutrally charged atoms. So for now, in an atom, neutrally charged, the atomic number is the number of protons and the number of electrons. So for this first example, we have Cu, which is copper, atomic number 29, which means it's going to have 29 protons, and it's also going to have 29 electrons. Element Ca, which is calcium, we have an atomic number of 20, so we have 20 protons and 20 electrons. Element P, otherwise known as phosphorus, has an atomic number of 15, and we have 15 protons and 15 electrons. Now, to determine the number of neutrons, we have to take a look at the atomic mass. Now, the atomic mass represents all of the mass in the atom, which is otherwise just the nucleons, or the protons and neutrons. And we know that the atomic number is the number of protons only. So if we subtract those two together, then we can determine the number of neutrons. The key here is with the 12.011, because if we follow this as is, minus the number of protons, which is 6, we'd get 6.011. We can't have 11 thousandths of a proton or neutron. So we round this number to the nearest whole number, which would be 12, and then subtract, and we would get 6 neutrons. So we'll determine each of the parts for each of these elements. First one here, we have potassium. We have 19 protons, which means we have 19 electrons. We're going to round this number, our atomic mass, to the nearest whole number, which would be 39. Subtract the atomic number, and we get 20. So we'd have 20 neutrons. Again, those numbers do not have to match. The next symbol here, Ca, which is calcium, has an atomic number of 20. So we have 20 protons, 20 electrons. We round the atomic number, the atomic mass, to the nearest whole number, which is 40. We'll subtract our atomic number to get 20 neutrons. Kind of a lucky element to come out 20, 20, 20. The last one is scandium. Sc has an atomic number of 21. So we have 21 protons and 21 electrons. We take our atomic mass, we round it to the nearest whole number, subtract our atomic number, and we get 24. So again, we're going to round our atomic mass to the nearest whole number and subtract our atomic number to get the number of neutrons. Now, determining the number of neutrons for each of these elements, feel free to pause this video, complete the question, and check your work. So for this first one, we would have had 64 minus 29, which gets us 35. This one we'd have 40, minus 20 to get us 20 neutrons. And we'll put a little n there to indicate that. And the last one here, we have 31 minus 15, which will get us 16 neutrons. Now, the atomic mass that's listed on the periodic table is actually the weighted average mass, what we call the WAM, weighted average mass of all the different isotopes of an atom. We saw in the simulator a moment ago that we had a carbon 11, we could have a carbon 12, we could have a carbon 13, and we could have a carbon 14. Only these two were stable, but the other ones do occur. But they occur at different abundances, and that's going to influence this mass a different amount depending on the abundance of each different type of isotope. Now, the mass number, when we see this term, this mass number, this refers to the mass of the most common isotope. So if we were to round And to convert from atomic mass to mass number, we just round the atomic mass to the nearest whole number. So this would become 12. So the most common isotope of carbon is carbon-12 because it has the most influence on the mass. So we find that the average is going to be closest to the most abundant isotope. So we round that atomic mass to the nearest whole number to get the mass number. Now we know that electrons are massless, so they're not going to influence the atomic mass, and that the atomic mass is the sum of the protons and neutrons. And this is going to help us with our understanding of isotopes, which are versions of elements that have the same number of protons, but a different number of neutrons. And this is the important part about isotopes. Now changing the number of neutrons will change the mass, and we see that represented in the top of our isotopic notation here. Carbon-12 has 6 protons and 6 neutrons. That's how we get to carbon-12. Carbon-13, again, it has to have 6 protons because it's carbon, but has 7 neutrons, so we get a mass of 13. And carbon-14, again, having 6 protons because it's carbon and 8 neutrons, gets us a mass of 14. Now this last one here is unstable, and it doesn't occur very much, but it does influence the mass because it is around. Now, isotopic notation, we're always going to write the mass number, which is going to refer to the specific isotope of that element that we're talking about. We don't write the atomic number. So we want to write chlorine 37 versus chlorine 35. And we can write that with just the symbol. And you can also see that sometimes just like this, where we have the mass number written, where the atomic mass normally goes. So you'll see it several different ways. But when you see the mass number there, it's referring to a specific isotope. All of our other subatomic particle calculations will remain the same. So calculating protons, electrons, and neutrons will remain the same as we have done prior. Now calculating the parts of these isotopes, chlorine 35 versus chlorine 37. Since the element is chlorine, we know that all chlorines are going to have 17 protons, because that's its atomic number, which means it has 17 electrons. And to find the number of neutrons, we're going to subtract our atomic number, 17, from our mass number, which is different for each of these two examples. So 35 minus 17 is going to get us 18 neutrons. And for chlorine 37, it's going to get us 20 neutrons. So the only difference between chlorine 35 and chlorine 37 are two additional neutrons, or 2 less neutrons, depending how you're talking about it. Carbon-12 and carbon-14, since we're talking about carbon, we have 6 protons, which means we have 6 electrons in a neutral atom. And the number of neutrons, we're just going to subtract from our mass number. Carbon-12 has 6 neutrons, the most abundant isotope of carbon, and carbon-14 would have 8. 14 minus 6 would get us 8. Now on to the last part. We're going to talk about calculating the average atomic mass, or the weight average mass of an element. And the atomic mass of all the elements on the periodic table is the weighted average of all the isotopes that we find in nature. This means that the isotopes that are more abundant are going to have a stronger influence on what that atomic mass actually is. And for example, since carbon-14 is not very abundant, it doesn't have a big influence on the average atomic mass. And we're going to use this equation here, which is kind of confusing. We'll break it down in a second, but this is not included on your reference table. So you need to make sure that you remember how to set this up. And really it just comes down to a average. So we'll look at 4 different isotopes of iron. Now we have mass numbers of the isotopes: iron 54, 56, 57, 58. We have isotopic notation in the middle column and their percent abundance. And we can tell just by looking at this that iron 56 is the most abundant at almost 92%, which means the average of all of these together is going to lie somewhere around 56, iron 56, because it is the most abundant. Now what we're going to do is we're going to take and I'll go back here and refer to this, we're going to take the partial percentages of the average of each isotope and add them together to get the total. So we're going to take the mass of the first isotope and multiply it by the percent abundance of that isotope over 100. And we're going to do that with the second isotope, third isotope, and so on. So for this first part here, we're talking about iron 54. So our mass is 54. And we take the abundance percentage in nature and we put that over 100. And a little short notation to do with this, what this is ultimately going to do is move the decimal in your percentage 2 spots to the left. So this becomes 0.05845. And that's a little shorthand, cut to kind of make this go a little bit quicker. You can also represent it over the 100, and you need to know it over the 100 because you do see some of these questions that come up like this, and you need to show the over 100 for the percent. Then we take a look at the second isotope, iron 56, and we take its percentage and put it over 100. And the same thing with the third and the fourth isotopes, putting their percentages over 100, making sure that we have our parentheses located here, and we're adding each of those partial averages together. And that gets us a weighted average mass of 55.910 AMUs, which is going to lie just below our iron 56. So you can see that the iron 56 is having the greatest influence since our average is just below that 56. Now we'll try another example. Feel free to pause this, try the problem, and check your work. A meteor crashes to Earth, it's collected and analyzed. Amazingly, a new element is discovered. Let's calculate the weighted average mass for this new element, UBN, based on the masses and abundances that are provided. And we're going to use our weight average mass equation. Now we have 3 different isotopes, 312, 313, and 315. So we're going to plug this in. The abundance of 312 is 37.26% over 100. We'll add that to the mass of isotope 2, which was 313, times that abundance, which is 2.79% over 100. And we'll add that to the third isotope with a mass of 315 times its abundance of 59.95% over 100. And when we punch this in, we get an average, and we can determine this ahead of time. We're probably going to want an average somewhere around 315 because it is 60%, but there's still a relatively large portion down at 312. So we're going to find an average somewhere in between these two, probably more towards 315 because it is a stronger or has a bigger abundance in nature. And our mass comes out to 313. And I'm going to give the hundredths place here. We'll round to that just so we can kind of see the effects on our average. And we'll call that 313.83 AMU. And if we were to round that up to 314, that's going to be close to our 315, which has the greatest abundance and therefore the greatest influence on our overall average. And we'll do one more example. Boron has 2 naturally occurring isotopes, B10, which makes up 19.80% of all boron atoms, while B11 makes up 80.2% of all atoms. What is the weighted atomic mass of boron? Take a second, set this one up, and we'll check your. Now I'm going to write this one in here in shorthand. We had our first isotope with a mass of 10, and we're going to multiply that by 0.1980. That's after we divided 19.80 over 100. And we're going to add that to our mass of 11 times 0.802. This is our weighted average mass. And that comes out to 10.802 AMU. And we'll round that to 10.80. So we see that that lies in between our 10 and 11, but up towards the 11 because of that stronger percentage or higher percentage, showing a greater abundance of B11 in nature. Now, when you do some sample problems, you're going to notice that you might not get exactly the same answer that's on the periodic table, like a atomic mass of 12.011 AMU for carbon. And that's because protons and neutrons don't weigh exactly 1 AMU. Neutrons weigh a tiny fraction more than protons do. So they're going to have a different influence on the actual atomic mass. But the way that we come up with this number, this atomic mass unit, it's actually an average mass from a carbon-12 nucleus, which would have 6 protons and 6 neutrons. Dividing that out, we get a mass right around 12.011. And since that's the most common isotope, we assume that with 6 and 6, 6 protons, 6 neutrons, that each one's going to weigh roughly 1 AMU, and that's the error, and that's kind of rounded off, and we just kind of assume that we'll treat protons and protons and neutrons equally in regards to their mass and call them each 1 AMU based off of this carbon-12 standard. If you guys have any questions, make sure you write them down and come see me to get some help. Have a great day.